Hmm. Anai and Bree, are you, let's see, you here yet? I see.
Yeah, I'm here.
Nice. Okay, good.
Yeah, I'm here.
Okay, good. Let's see, everybody's coming in all at one time. Okay, Jennifer, I finally got you in. Can you hear me, Jennifer? You okay? You there?
Yep, I can hear you.
All right, good. Okay, so I got Jennifer, Anai, Bree, Tori, Haley. Oh, all right, guys. I tell you, we'll hang on a few minutes before anybody until everybody gets here. My internet's a little bit weird this morning. I got bumped out of my first class, but that gave me a chance to breathe. So if I get bumped out, guys, hang on. I'll do my best to get back in. I don't know what's going on today. The first shock I got this morning was opening my computer and it said, "You have no internet connection." And I'm like, "Oh, no, 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 no." So, but I don't know why it was doing that, because as soon as I booted it back up, it said it was fine. I have no understanding of what the technicalities of being on the internet are, except that sometimes I get bounced, and you do too. Okay, Michelle's here. All right. Guys, the first thing, while we're waiting for everybody to get in, the first thing I want to show you is what I've done on the key. I meant to send out an email last night to tell you that I had the complete key to the review sheet online now. But let me share the screen and show you that, because it's a little bit of a jumbled mess, because I didn't do the problems in order. I don't know why I didn't do that, because I didn't want to waste paper. It's Earth Day, by the way. So for the first time in years, LA has seen blue sky, and you can see monuments in India through the haze. There's no more haze, which is an interesting byproduct of, particularly on Earth Day, of being not able to drive your cars. And that's an argument for transportation. That's not everybody has to get in a car and go somewhere. So. And it says my meeting should start in a few seconds. So let's see what's happening here. Okay. iTunes. I don't care about iTunes. There we go. All right. Okay. So so let's take a look at what I've got here. And I don't want the iTunes thing bouncing all around, so I'm going to move that away. Whatever. Do whatever you want to with iTunes. Okay. So let me show you what I've done, and we will work on this. We may start working on it today. If you've got general questions, we will probably spend at least half the period working on some more of those word problems, because I think those are, in a way, I think those are the hardest things on the test, because I think it's sometimes harder to do those than it is to do the business problems, for example, because the business problems are kind of, here's the revenue, here's the cost, write the profit, that kind of thing. They're pretty straightforward. But here, let me show you what I've done on the test key. Okay, so guys, even when the answers were in the back of the book, I provided the detail. Okay, so it's a little messy, and for some reason I can't quit writing up from left to right. I can't write straight. I guess if I was left-handed, I'd go the other direction. But anyway, you can think about it like this: my handwriting is increasing left to right. So Stephanie's coming in. Let me get her in. Okay. All right. And Lainey's there. Get everybody in. Let's see. Stephanie's in. I don't know about Lainey. Just having trouble getting her in. Oh, shoot. For some reason I'm having trouble getting people in. Probably slow internet. She's still waiting. All right, now I think she's in. Yeah, she's in. Okay. All right, so I got everybody that's waiting in. Okay, guys, so here's what the key looks like. As I said, even on the ones that had answers in the book, the odd ones, I provided the detail. And when I did all that, this is a long review, but I can tell you, if you understand everything on this review, you'll be fine. Okay, so pick and choose and check your answers and so forth, and we'll talk about these if you have questions on whatever later today and tomorrow mainly. And then Friday, as I said, we'll have an optional period at the same time, same place, 11 to 11:50 if you have more things you want to talk about in terms of the test. And then I will post the test Friday, and it will be due before class on Monday morning. So you've got plenty of time to work on it. It will be like the other ones. It'll be open notes, open book. You can work on your homework with other people. I don't know how many people are doing that in this class, but I don't want you talking to anybody else or using any internet sources to do your test. You should have plenty of examples and to do these with. So what I did on this, I had to omit a couple. So look before you try. This was one I didn't realize it, but it's not one we can really do based on what I've talked to you about. I tried to go through. Initially, I did 1 and 2. There was a lot of stuff in 2. Then there was 3. It sort of separated out some of the increasing, decreasing from some of the concavity things. So remember that if you want increasing, decreasing, you're looking at the first derivative. If you want concavity, you're looking at the second derivative. If you want maximums and minimums, you're looking at the first derivative. If you want things like point of diminishing return or inflection points, that's the business application, you'll look at the second derivative. I've written that all the way through this sheet, so take a look at it. So I got to number 3 in order, but then I went down to number 6. And then I went down to 8. So keep looking through. There's one, that 8 was a point of diminishing return, so I pointed that out there. I then came back to 4. The reason was, what I did, guys, was on those long ones where I asked you to do everything, I just started on a separate sheet of paper regardless of what number I was at. All right, so there's all of number 4. All that most likely is what you're going to be looking at on the test. I'll give you a function. I'll ask you everything I can think to ask you about it, from domain to increasing, decreasing, local max, local min, concave up, concave down, endpoints you want to test maybe for maxes and mins, absolute maxes and mins, and so on. But there's one of those. I want you to look at this one in particular because it shouldn't take you very long to do it if you know what you're doing. I don't give you a function, but I give you how the function's behaving. So you can draw the line from that. So take a good look at 5 when you're looking at these things, and we'll go over that later. There's the picture. 7 is one with asymptotes. Again, with asymptotes, most likely because the functions tend to be a little more complicated, I will give you derivatives typically, and you'll just have to know, what do I look for in the derivative? You don't have to bother with taking it. You've got the information there. So when you look at that, think about that. The last one, I think this is the last one, point of diminishing returns is a second derivative. All right, so keep that in mind. Okay, so any questions about the review and reviewing for the test? Otherwise, I'm gonna go back and we're gonna work on some more of those word problems. Does anybody have a question? That's posted on Moodle, so you can get it there. I want to talk about the optimization problems again. And this is the last one we did yesterday, and I did not finish it. So I'm going to finish this one up, and then I'll open up questions, open up the floor for questions, and then maybe do a few more examples. Let's review what we said about this one, because this one was a hard one because it was hard to maybe draw the picture. It was the one where we wanted to build a box, and this box here, remember I drew a rectangle right there and a rectangle right there and sort of connected the edges of it, and we have a box where actually, if I look at this thing, you can sort of think of it here as this is the length right here, this is the width, and that's the height if you want to think about it like that. And you could have labeled it like that if you wanted to. The length the width and the height. But in reading through the problem, what they said, let's go back to that for just a second. What they said was we want to minimize the cost of a box made from thin sheet metal. The container will have a square base, so that way we know the length and the width are the same down here. That's why I labeled them both as X. And a top and a bottom, of course, and must have a volume of 36 cubic inches. Now, when I'm writing down all the information, that volume of 36 cubic inches doesn't look very important, but it turns out to be important in a minute. And I'm going to remind you of why that is in a second. I think I probably need to get rid of some of this, all this stuff that I wrote all over it. Let me see if I can erase some of this so it doesn't look so bad. Let's get rid of that. And I'll point it back out again. Oops, got rid of something I didn't want to get rid of. Right there. Okay, so we're trying to minimize the cost of the box. And the cost of the box has to do with how many square inches are in it. So that's what we're looking at in this first equation. So if I want to minimize cost here, if I look at the base, and I'm going to shade it here, right, guys? And you have to see that sort of in two dimensions. If I had a base that looked like X times X, the square inches in it would be X times X. It's like if it was 2 times 3, it would be 6 square inches. So X times X, and each square inch costs 12 cents. That was for the top, and the same thing happened for the bottom. Well, I had the bottom first, top and the bottom. So both of those have the same square inches in them, okay, and both of them cost 12 cents. The sides now are a little different. If you look at the sides, that side right there is X, and that side right there is Y. And that's what happens on every single side, X and Y, and there's a front, a back, and 2 sides. Or you think about it as 4 sides of the box. So, and the square inches in those was X times Y. Those sides cost 9 cents each to produce, so per square inch. So I've got 4, that's the square inches right there, and that's the 9 cents per square inch. Okay, and the 4 is because they're 4 sides, guys, and each side is X times Y. So what I came down with is that I'm trying to minimize that function right there. Okay, now here's what we said about these kind of problems. I have to, in these problems, I have to get it in terms of one variable. And what you're looking around for here then is something that connects X and Y. And that's why you need to write down things that you see immediately in the equation. Here is something right here that connects X and Y. I could take this easily and solve for Y, and that's my connection between X and Y. And it's exactly what I'm going to plug in right here for Y. See, there's Y right there, and there's what I'm going to put in the place of Y right there. Okay, that's basically where I got to yesterday. I did no calculus on this thing yet. Let's simplify it a little bit and see if we can go further with it. Again, the 24x squared was the cost of the side, the top and the bottom. If you did this one, this was the 36 times xy, and so that meant I had a 36 times x, and the y was 36 over x squared. Yesterday we multiplied it out, and I think we said it was 1296. I think I made a mistake on that to begin with. That's 1296 there. And so there's the function you're trying to maximize or minimize. Okay, in this case, we're trying to minimize because it's cost. All right, so I'm gonna write in this blank space down here where the other problem is, but I'll get rid of it in a minute. Let's see what we got. C is 24x squared plus, now I've got to take the derivative of this thing So I'm going to take that 1296 over x and bring up that power. Test 2 tested you on your derivatives, and you know what we've got to do to take some derivatives is rewrite them. If you have x's in bottom, you have to bring them up as powers, as negatives to the top. If we have radicals, we need to write them as a power, because all we really have to work with is the power rule and the quotient rule and the product rule. So I'm going to take the derivative. Once I get the function that I want to minimize or maximize, this first derivative is easy. Anybody, cut your mic off and tell me what the first derivative is. Anybody?
48x.
Okay. 48
minus 1,296 x to the power negative 2.
Yes. Good. Good. Good, Nine. So what we've got is there's the derivative. Now, so all I have to do at this point, remember that from all the graphing stuff and everything we've done, we know that minimums and maximums happen where this is 0, where the derivative is 0. So now it just becomes an algebra problem, guys. And if I'm going to solve this equation right here, I'm really not going to want this negative power in there. So I'm going to rewrite it again to do something different with it. Now I'm going to try to remind you of some algebra. Or maybe you can remind me. A lot of times when I have fractions or denominators in a problem, I'll try to clear them out. In other words, I would just as soon not deal with that fraction right there. I can do one of two things. I can find the common denominator, or I can clear out the fraction. What I prefer to clear out the fraction here. What would I need to multiply both sides of this equation by to clear out this denominator right here?
X squared?
Yeah, if I multiply both sides by x squared, it's certainly not going to affect the other side, okay? And if I keep looking at it, this will be 48x cubed minus 1296 minus 1296, because the x squared, see this, the x squared canceled out. That was my whole idea here. I just want to get rid of that. So I multiplied the whole thing by x squared, and then on the other side it is 0. Now, there are a lot of ways to go from here, guys. Somebody give me an idea. Somebody tell me, think algebra and tell me what you might want to do to solve this equation. It's not a quadratic, so we're really thinking maybe we can, I don't know. I'm not even going to give you any ideas. What do you want to do?
Could you add the 1,296 to the other side?
All right, that seems reasonable. 48 x cubed is 1296. Okay, Haley, your idea, that's a good idea. There's another simple thing we can do to get closer to what x cubed is. What do you think I should do next?
Divide by 48.
Yeah, let's try to divide by 48. So guys, in algebra, if you don't know what to do, just do something, okay? So we get x cubed is 48, the 1296 divided by 48. Let me get my calculator, otherwise known as my phone right now. Or you guys tell me, what's, give me some feedback. Hang on. All right, tell me what 1296 over 48 is. Anybody got it? 1296 over 48. I'm gonna cut this off. My phone's causing some kind of feedback here.
27.
27? Okay.
Yeah.
Oh, well, actually, that's good. Because what's x?
Cube.
X cubed is 3, right? So x is 3. That's the part of the, I need that, okay? And I'm gonna go back to my picture. I now know one of the dimensions of the box. I know that that was in inches. So that's where a minimum is gonna happen. We could check it on either side, but that's where a minimum is gonna happen. I'm gonna scroll back. Is everybody okay with solving the equation? You gotta be careful with that. So that's where the algebra comes in. So let me scroll back. I know that x is 3. That tells me in my picture here, I'm gonna try to erase some of this stuff. You know what? I'm gonna draw the whole picture over again, because I'm gonna label it so we can see what it was. Now,
When you do the square root and you get 3, you wouldn't take the -3 because you have negative sides, right?
It's not a square root, Haley. It was a cube root.
Oh, okay.
Okay, so it's the only thing it can be is 3. It couldn't be
Okay.
-3. Okay? Okay. So here's, I'm gonna draw a box again, guys, so I can refer to it. We'll practice drawing boxes. So the way I drew it was I drew 2 sort of overlapping squares. I had here, 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 and here. We had labeled the base x, x, and the height was y. And we labeled the base x and x because we knew it was a square base. So now what I know is that the bottom of this box is 3 inches by 3 inches. Okay? Now, the question is, how do you find y? Well, you had a connection between y and x here. So if x is 3 inches, then what I would have would be 36 over 3 squared. So y, in this case, would be 36 over 3 squared, which would be 4. That tells me that this box is 3 by 3 inches on the base and 4 inches high. Okay, and does it contain 36 cubic inches? Yeah, because 3 times 3 times 4 is 36. It's 36 cubic inches. Now, question about that. I got one more thing to do with this. That's not an easy problem necessarily, but you cannot bite these things off and try to swallow it in one chew, guys. You got to write down things that you know. You got to try to find out a function for what you're trying to minimize or maximize. Then you got to think about taking the derivative and so on. So take it a little bits at a time. 3 by 3 by 4. Now, the person who's manufacturing this, you say to them, well, you just need to make a 3 by 3 by 4 box. But then the next question they're going to ask is, well, what's it going to cost me? Because I was trying to minimize cost. Well, if you want to do that, you go back to whatever the original cost function was before you took the derivative. And this is in cents because it was 24 cents and that was 30 cents or 12 and whatever. So I would put in for the cost. Let's see if I can find any more space here. 24x squared plus 36xy. Gosh, I'm doing everything. 24x squared. So it's 24x squared plus 36xy. This will be the cost in, I'm minimizing cost here, so that'll be 24. We found out that what minimized the cost was a 3 for x. So 36 times 3 and a 4 for y. And so the cost here would be 9 times 24 plus 12 times 36. Help me out with that, guys. 12 times 36. Ooh, so, did I do that right? That's 24, 9 times 24, and that's 12 times 36. Figure out what that is, guys, for me, please. Give you something to do here.
And this is finding
The cost. This is actually finding the actual cost here, okay, that it costs to make it. So how much do we get there? 180. Anybody got a value on that? Emily, have you got your calculator? Have you got it, Emily?
I have 600.
Yeah,
Okay, Emily, what'd you get? And then I'll check with whoever else has got it.
I got, well, then I entered it wrong, so I got a weird number.
So 9 times 24 plus 12 times 36.
648.
How much?
648.
648. Emily, is that what you're getting? I'm just multiplying This times that.
648, yeah.
648. Okay. So this may be a total cost or whatever, but it was in cents, remember? So that's like, if I do it in cents, it looks like that. If I do it in dollars, it would be $6.48. That seems like a lot for minimizing cost, but it's a minimizing total cost of doing these boxes. Okay. 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 So there's a couple more of these things I want to look at, but before I do that, I want to see if you guys had any ones you worked on from the homework that you'd like to see. And if you do, I'll do those first and on my book, and I will I'll do these other samples of mine later. Does anybody have any that you saw in the homework that you wanted to look at? I've actually picked out a couple that are like the homework. So if I do those, you might be able to go back and do your homework and do it a little better. Anybody? Okay. I'm gonna give you a second to write that down, guys, because I'm getting ready to erase it. It'll be on the video, but I'm getting ready to erase it because I want to do another problem. Not necessarily that one. Here, I'll just leave it there. I want to do the next one under this one, which has to do with peach trees. This is another way, another strategy for solving these things. So there was the end of that. So everybody got what they need? It'll be on the video if you want to watch it again. All right, I'm gonna look at this next problem. Okay. So, so this next problem is a little different from what we've been doing. We've been able to draw pictures. This one, I'm not sure I'm gonna be able to draw pictures. Let's read it together and see if we understand what it is we're trying to do. It says 25 peach trees are planted in a certain area. If they're planted in a certain area, you'll get, say, an average of 370 peaches per tree. If you add an additional tree per acre, you reduce the yield. In other words, if you did 26 trees, you would only get 360 peaches. So you're reducing the yield by 10. Too many trees on the land. Maybe not too many. Maybe by adding one tree, that additional yield from that one tree will give you more peaches. But at some point, if you add too many trees to the land's not going to produce very well for you. Okay, so the idea here is to ask the question, how many trees should I plant per acre to maximize the total number of peaches? Now, you read that and you say, well, I don't know what to do, but get a handle on what you're trying to maximize. Total number of peaches. And you got kind of a hint in the first sentence. If you had 25 trees and every tree produced 370 peaches, how would you find out what the yield was? Now, yield means how many peaches, guys. How would you find out what the yield was if you knew you had 25 trees and it was 370 per tree?
25 times 370.
Exactly. 25 times 370. And I'm gonna say something that's ultimately true, and it's part of your learning experience. I can get every one of you guys to do this problem perfectly if I ask you the right questions. So your task as a student in learning how to do this is ask yourself the right questions. If you ask yourself the right questions, you'll have an easier time finding out what the right answers are. So the first thing I'm going to write down here is the yield in this example that they gave me. Now, again, yield, that doesn't look right. I before E except after C. Okay, let me do that again. That spelling. The yield is the number of trees times the number of peaches. Number of trees times the number of peaches. Now, every one of you could answer that question. You'd say, that's an easy question. Okay. Every one of you could do that if I ask you the right question. Or if you were standing out in a field saying, there's 5 trees, I'm going to get 50 peaches off each one. I'm going to have 250 peaches when I go home. Okay. So what I need to do is figure out a generic equation for this thing about what's happening here with the peaches. So one way to do problem solving is to make yourself up an example. So one thing we know, if I sort of make a table here, and I put trees on this side, and I put peaches on this side, I might even be able to solve the problem like this, but it would sort of defeat the purpose of having calculus. But if I have 25 trees, I will have, per tree, I would have 370. And we know that we would multiply that times the number of peaches and I'd have that. Now, here's the trick here. You guys told me, or I said it, if you add 1 tree, how much was your yield going to go down? If you added 1 tree to this, how much was your yield going to go down, guys?
10.
10 peaches. So for that 1 tree, it went down 10 peaches. Okay? So, okay, my yield then would be 26 times 360. Let's do this. Let me just sort of show you what's happening here. Tell me what 25 times 370 is. Anybody with the calculator, tell me what 25 times 370 is.
9,250.
Okay. Got confirmation on that? That look okay? All right. In this one, it'll be 26 times 360. Right, so somebody find 26 times 360 for me. 26.
9,360.
Good. Okay, look, it's going up, isn't it? It is going up by adding a tree. Let's look at the next one. 25, if I add 2 trees, it's going to be 370 minus 2 tens. Now, it's kind of important that I'm kind of splitting this apart. Normally, you might jump the gun and say, oh, it's just 20. I'll just subtract 20. It'll be 350. But what I'm looking for, guys, is a pattern. Mathematics is about patterns. And equations like this are about patterns. All right, so tell me what that one was. It's 27 times 350.
9,450.
9,450. Okay, it's still going up. So it looks like I should try to keep adding trees, but I don't want to just do this. I want to see if we can figure out a way to generically do it. Maybe you can see the pattern at this point. We'll do one more. 25 plus 3. I add 3 trees. That's going to be 370 minus 3 tens, because my production will drop, or my peaches per tree will drop 10 per tree. So that's going to be 28 times 340. What's 28 times 340?
9,520.
Still going up. Still going up. All right, now, here's what I want to do. I want to try to get a pattern here. And that pattern is going to give me an equation. So let's look at our table and see what happened. When we added 0 trees to this thing, I didn't take away any peaches. When I added 1, I took away 10 times 1 for the 1 tree I added. When I added 2, I took away 10 times 2 for the peaches. For 3, I took away 10 times 3. Now, it looks like the thing that's changing here, what's that 1 plus 2 plus 3? What did I say I was doing when I added 1, 2, and 3? In the context of the problem, what was 1, 2, and 3?
You're adding another tree?
Yeah, the 1 was adding 1 tree, the 2 was adding another tree, the 3 was adding another tree onto those. So the question is, how many trees do I add to get this to a peak number? So I'm going to make this generic by saying, okay, I don't know how many I'm going to add. I'll just call it X. The question is, how many trees do I add to get to this peak? Now, we know that to find yield, we need to multiply trees times peaches. So the pattern for the first column looks like that. do you see a pattern for the second column in terms of the number of trees you added? What's the first
So-
number always in that column?
Would it be
370.
370 minus 10 times x?
Okay, all right, that's 370. Yep, it's always the same. This one changes every time. Every time I add a tree, I put 1 times 10. There's a 2 times 10. So x was, remember, x was the number of trees I added. And I heard the answer. The number of trees added. I'm not writing very well. So I think this is going to be, you're going to reduce your peaches by 10 times the number of trees you add. See the 1, 2, 3? That's what my x is. I'm following that pattern right there. Okay. So I have actually an equation here. These are trees. These are peaches. Based on how many trees you add. That is an equation for yield. That's an equation for yield. Guys, in your homework, you want to try one of these? I think there's a problem about apples or something. Apples, peaches, I don't care. It's the same idea. Make a pattern. All right, so I have the equation that I want to maximize. I really want to maximize yield. There's that equation. Okay, guys, what do I do to maximize a function? This is the whole crux of what we've been doing the whole ever since we got booted off campus, okay? What do we do to maximize a function?
Well, first you would like combine like terms, wouldn't you, in the equation?
Yeah, I think that might make it easier for us, but once I do the algebra on it, guys, what do I actually do calculus-wise?
Derivative?
Take the derivative. Derivative is the thing that maximizes and minimizes things. So I think what Haley was saying is it might be easier to multiply this out first. Is that what you were saying, Haley?
Yeah.
Okay, let's try that, guys. So I'm going to write 25 times 370, and I'm going to leave it like that for a minute. And then it'll be minus 250x, because I'm multiplying 25 times this, and 25 times that. So 25 times minus 10 is minus 250. Then I'll multiply this, 370x, 7, minus 10x squared. All right, I multiply this times this, that's right. And then 370x, and then minus 10x squared. So let's look at the equation. 25 times 370. If I add these two terms, let's see, 370 minus 250 is going to be 120x minus 10x squared. Oh, it's plus, sorry, it's plus 120x. It's plus 120x. Now, you might say, well, do you want us to multiply out 25 times 370? You know, not yet, because I know I'm going to take the derivative next. And what's the derivative of that? Whatever it is, what's the derivative of that number right there?
Nothing.
Nothing, 0, exactly. So I'm going to spend my time doing that. So y prime is derivative of that's 0. So that's 0. The derivative of 120x, what's the derivative of 120 times x, guys?
120.
120. Derivative of minus 10x squared? Minus 20x. Yeah, minus 20x. Okay, what do I do once I've got the derivative? If I'm trying to maximize or minimize something, what do I do once I take the derivative?
Set it equal to 0.
Yep, I find a critical number. Same old, same old. Critical number. I'm going to solve this thing. That says that x is 6. If I were to look at this on a number line, plugging it into the derivative here, if I factored it, you'd see it as well. I moved it over, but I could have factored a 20 out of this, guys, and gotten 20 times x minus 6. And then the critical number you could see is 6 as well there. So for the right of 6 is positive. To the left of 6 is negative. All right, actually, is that right? 6 positive, negative. Okay. All right. So, whoops, I made a mistake. Look at this. If I plug, I was wondering, that's coming out to a minimum. That's not what I'm looking for. Let me show you how I made the mistake. I made a mistake in a factoring. If I were to factor this, guys, if I took the 20 out, so be careful with your factoring. What's left if I took the 20 out? First, I would have a 6, and then I'd have minus x. That's going to turn the signs around here. Okay, so that's the mistake I made. When you draw your number line now, you'll have a 6, and to the right of 6, that would be negative. To the left of 6, say at 5, that would be positive, and times 20 is still going to be positive. Increasing, decreasing, we got a maximum there. Now, what did the 6 stand for, guys? What did the x stand for? I haven't finished the problem until you tell the farmer what he needs to do, not with an equation, but in words. Okay? What does the 6 stand for? What should I say to the farmer? You should do what? Let's go back. What did the x stand for? What did that x stand for right there?
Number of trees.
The number of trees beyond 25,
25.
right? The number of trees beyond 25. So this says you should plant 6 more trees past the 25. So if I do that, the 6 more trees means I'll plant 25 plus 6 is 31 trees. Okay. And then that means I would reduce my yield by 370 minus 60 because remember it was 10 less for every tree. So that's 31 times 310. What's 31 times 310? Now I do want to know that, guys. What's 31 times 310? Anybody? 31 times 310. Anybody got it?
9,610.
9,610. That sounds about right. Now look back at where I was practicing up here. Notice it was going up. 92.50, 93.60, 94.50, 95.20. I could have put in 3, 4, 5, 6. It turns out that when I put in 6, this is what we're going to call the maximum yield. That's the maximum number of peaches I can expect to get. If I add one more tree, let's look and see what would happen. What I expect is that the yield's going to go down because we said that was the maximum. So if I added one more tree after 6, it'd be 25 plus 7 times 370. 7 trees means I'm taking 70 peaches away per tree. That's 32 times 300. Tell me what 32 times 300 is, guys. I think I know, actually. I think that's 9,600. Is that right? 9,600? See, 006, 9,600. Notice, now I had reached my peak right here. It's going down. Okay? So read the problem. Try to figure out maybe using a pattern or drawing a picture. This is no good picture for this, but drawing a pattern, seeing a pattern, trying to figure out what you're trying to do. Write as much stuff as you can down. Write a picture if you can write a picture down. See if you can put it all together.
So it would be 6 trees.
Yep, it means add 6 onto your original 25. So you're going to tell the farmer you need 31 trees per acre, and your yield is on this with these 31 trees is going to be 9,610 peaches. Of course, that's fictitious because some of the peaches rotten. People come steal them or whatever happens. But anyway, that's what ideally would happen. Okay. All right. I think there's one other problem I want to do in your book, and it's another fence problem. I think those ideally or generally are the easiest ones, the fence problems. These that you have to kind of work out the pattern are a little harder. But let's do one more in the book here. And maybe you've tried this one. And in my book. Hang on. In my book. Guys, there was a book. If you've got your book, open your book to the section where this stuff was. I can't find it. Everything I own is on this counter, and I still can't find my book. I think there was a problem that looked like this. So, and it was one of the first ones. And it said you want to build an enclosure that looked like that, which had fence on all sides and a fence down the middle. Excuse me one second. Let me see if my book's under some pile here somewhere. Here it is. It's on the couch. All right. So this stuff was in 3 point, where it is? 3 point, I'll find it. Summary 3.5, I think. Not quite, 3.5. 3. Actually, it's in 3.4. And I'm looking at number 5. Okay, this is number 5, and I think I may have assigned this one on page 201. It's on page 201. And they have this, they say a rancher has 200 feet of fence. So we'll write down the important things. 200 feet of fence. All right. And wants to enclose 2 adjacent corrals. What dimensions should be used so that the area will be maximum? Now, they draw a picture in there for you. When they say 2 adjacent corrals, that just means one enclosure right beside the next one. I'm going to keep pigs in this one and horses in that one. Whatever. Anyway, I need a fence down the middle. I want to maximize the area. Now, they actually labeled it for you. And the way they labeled it was like this. And they had one side Y here. But if that side's Y, then both of these are Y because it's just a nice rectangle. So I need fence on every one of those pieces. So regardless of the calculus here, guys, how much do every one of those pieces have to add up to? I gotta label things. So how much should that add up to? How much fence does he have? How much fence? It has 200 feet. That's 200 feet. Sometimes I feel like I'm in Ferris Bueller's Day Off when I'm doing this. Okay, it was like, remember the guy that kept saying, the answer is, the answer is, the answer is. Okay, he's got 200 feet of fence. So if you added up all of these things right here, what would it be? Add up all of those things right there. That's all perimeter there, guys.
4x plus 3y.
Thank you. 4x plus 3y. Now, before we go any further, that's a connection between x and y. We're going to need that in a minute because remember, a lot of these problems you had to write the thing you're trying to maximize or minimize in terms of one variable. What they're asking you here is to maximize the area. Maximize area. I need to write an equation for the area. And there are a couple ways to go about doing this. I mean, disregarding how much space that takes up, tell me what you would do to find the area. Anybody, tell me what you would do to find the area. What's the area of this enclosure right here?
X times y.
What's the area of that enclosure right there?
X times y.
X times y. How many enclosures do you have?
2.
So what's the total area?
2x Y.
Exactly. Everybody see what I did? Now, some people might say, well, I'll just do it with both sides. Well, x plus x is 2x. If you want to do that whole side times y, it's still 2x times y. But if you want to do it an enclosure at a time, you can do that. Now, I'm trying to maximize that. It needs to be in terms of one variable. Here is how I'm going to get a hold on that. I am simply going to solve this for one or the other, x or y. Let's solve it for y. If I solve it for y, it'll be 200 minus 3y equal 4x. Did I say I was going to solve it for y? I just started doing something else. Let's do this. I'm going to solve it for y. I'm going to move the 4x over. So maybe I did it. 200 minus 4x equal 3y, which means y is 200 minus 4x over 3. Y is 200 minus 4x over 3. What I intend to do here now, guys, is write this equation that I'm trying to maximize in terms of one variable. There, right there, I'm going to put that in the place of y. And I will just have one variable. That's what I need. So here's what I've got. Area is 2x. 200 minus 4x over 3. Okay, everybody with me? I did that because I knew the perimeter of the fence, and I knew how much fence, and I knew the connection between x and y. I want to write this in terms of one variable because ultimately what I want to do is take the derivative. Now let's prep it for the derivative. I can bring this 3 out and write that as 2/3 if I want to. And then I'm going to multiply the inside by 2. I mean, no, I've already got the 2/3. I'm going to multiply the inside by x. So 200x minus 4x squared. Okay, that just makes it a little easier to differentiate, guys. I'm just multiplying this out and then pulling out the 2 and pulling out the 3. All right, once I've got the thing I want to maximize, what's the next step? And then we all go have lunch. What's the next step? Always, you're doing calculus. You're doing calculus, you're doing derivatives. Yep. So that says a prime. 2/3 is just a constant, guys. I don't need to worry about that. The derivative of 200x is 200. Derivative of minus 4x squared is minus 8x. Once I take the derivative, 2/3 is 2/3. It's not going to make any difference. I need to find out the critical numbers. In other words, I need to find out where this thing is 0. That'll tell me where the maximum happens. So I'm going to take the 200 minus 8x, set it equal to 0. That'll be 200 equal 8x. X is 200 divided by 8. That'll be 25. Okay, let's see what we've got. That says, and that's going to yield a maximum. If we go back to my picture, it says I need to make each one of these x's 25. 25. 25. What does that mean about the 3 y's? How much fence have I got left to go around for the 3 y's? Well, how much fence did I have in the beginning?
200. So now you have 100 left.
I have 100 left for those 3 y's. So I'm going to have to split it 3 different ways. So if I take away the 100 that I already used on the x's, I've got 100 to use for the y's. Divide by 3. Each one of these should be 33 1/3 feet. I guess that's what it is. 30. It's in feet, I think. Okay, 33 1/3. Okay. All right, guys. Tonight I want you to work on finish up on these, but go back and start going through that review sheet. Okay, and then we'll talk about it tomorrow. And we'll do as much as we can tomorrow. We'll get more done if you ask me questions about things you don't understand rather than just saying, let's just go through the whole sheet, because it's going to take a little while to do that. So look over it, look at things you understand, things you have questions about, make a list of those questions, and we'll do them then. Okay? Is everybody okay? All right, go have some lunch. I guess you're not, are you unhappy about not being able to eat in the refectory? In a way? No. Okay, Emily just shaking her head. No. Okay, maybe get better food at home. I don't know. When I'm cooking for myself, I wonder about that. But anyway, all right, guys, I will talk to you later. We'll see you tomorrow at 11, okay? Bye.